Alright, welcome back. Here is the video for September 22nd. Still talking about functions of multiple variables, getting started with the fundamentals. And today our goals are to talk about really creating the graph, creating visual representations of multivariable functions. We're going to talk about how to graph multivariable functions using technology. By the end of the day, we should be able to match the graph of a multivariable function to its equation. We're going to introduce some terminology, in particular the terms label curve and contour map. And we're going to draw a contour map and we're going to match that map to the equation and or graph of a multivariable function. Okay, now to set the stage here, I want to talk about how we traditionally draw the x, y, z axes. You see, when we were in single variable land, y equals f of x, we had one axis for the input variable, and we had one axis for the output variable. Now, in the case that we have a function with two input variables and one output variable, the total number of variables in this equation is 1, 2, 3. Because of that, if we're going to start to draw the graph of this function, we're going to need 1, 2, 3 axes, and our drawing is going to be three-dimensional. Now here's our convention. We start out with two perpendicular axes as if we were drawing the xy plane. And then the goal is to draw a third line which resembles a line which is coming toward you, the viewer. Now in practice, this means drawing a third line that comes out at a slight angle, maybe a 30-degree angle with this horizontal line here. And this is just enough to create a sense of perspective that maybe this line on a slant is coming toward the viewer, and then you have these two crossed lines in the center. Now, it's a little bit unexpected how we actually assign these axes to variables. The tradition is that this axis that is coming toward us actually represents x. X is the line that's coming toward us. And the closer it gets to us, the more positive x becomes. As we move away from ourselves in the view, this becomes more and more negative. So here would be, for example, x equals positive 1, but in the back would be x equals negative 1. Now, where is the y-axis located? The y-axis is located on the right-hand side. X is coming toward us, y is off to the right, and the positive y direction is the right-hand side. So this would be y equals positive 1, and here is y equals negative 1. And then finally, the up-down axis, the vertical axis, represents the z-coordinate. And so we have z here, positive 1 going up, z negative 1 going down. So this is our convention when we draw x, y, z axes. Unless something otherwise is specified, x is coming toward us, y is to the right, and z is straight up. Okay, so let's go ahead and let's try and sketch the graph of f of xy equals the square root of 4 minus x squared minus y squared. And perhaps before we get started, let's just draw maybe 1 or 2 points of this graph by ourselves, just to get an idea of what the graph is really telling us. So let's get in, let's draw our x, y, z axes. And let's go ahead and let's plug in the point, say let's plug in the point 0, 0. If I evaluate that point, 0 in for x, 0 in for y, then I'll get the square root of 4 minus x squared minus y squared, except not x anymore, not y anymore, but this time 0 squared. This time 0 squared. So the associated output is the square root of 4 is 2. Now, with an input of xy equals 0, 0, and an output of 2, the point 0, 0, 2, x, y, and then the output for z is on the graph. So, in order to plot this point, I would go 2 units up on the z-axis. I would not go any points in the x or y direction, and I would plot the point 0, 0, 2 up here. Now, just for another single point, to get our mind straight, we will get the point, for example, xy equals 2, 0. Let's plug that in. F of 2, 0 is equal to the square root of 4 minus 2 squared minus 0 squared. Now 4 minus 4 minus 0 is 0. So the associated output would be 0, square root of 0 being 0 as well. So that means that the point x equals 2, y equals 0, z equals 0 is on the graph. And to plot that point, I would go back to the graph, and I would go 2 units in the positive x direction. I would go no units in the z direction, no units in the y direction, and I would sketch in that point, 2, 0, 0. But because there are an infinite collection of x's and y's, which are possible inputs for this function, just plotting points is going to not really be an effective way to get an idea of the shape of this graph. We've already done 2 calculations, it's already taken several minutes, and I still have absolutely no idea what the graph of this function is supposed to look like. And that's where we're going to have 2 tricks to help us to get a clearer idea of the shape of the graph. And the first is to use technology to help us to graph the function. So let me go ahead, turn off inverted colors, and let me go out to Google here. And all I have done is I have simply Googled graph multivariable functions. And here I think are the 2 sort of prime best resources for graphing functions of 2 variables. I'm going to go ahead, and I have a slight preference for GeoGebra's 3D graphing calculator. Alright, so that brings us to this screen here. Hold on, I'm going to dock this tablet on my keyboard, and I'm going to type in the formula for the function that we had, which is the square root of 4 minus x squared minus, let's come on down here, minus y squared. Okay, and it's automatically graphed in blue. Here, the surface that we get, the graph of this function. Now this is quite nice because if you hold down the right mouse button, you can rotate this picture at will. And so you can get a pretty nice sense of what this graph looks like. The collection of all points x, y, and z, which satisfy the equation, form the shape of a hemisphere, the upper half of a sphere-shaped shell, in other words, which has radius 2. Now, one of the things that is a little bit obscure about this particular website is, for some reason, it has the positive x direction going toward the back. I'm not exactly sure why they have chosen that, but you can rotate it to reorient it in a more natural way. You have positive coming toward you, positive to the right, positive going up, the more conventional way. All right. Now, you can just play around with this and you can have as much fun as you like. For example, you can ask yourself, what would happen if I just took the square root off? If I just did 4 minus x squared minus y squared. And that is now graphed in red. Unlike the blue surface, the red surface is a little bit more pointy at the top, I would say. It's looking a little bit more like the end of a pencil or maybe a marker than the previous surface. Another major difference between red and blue here is that the domain of blue is quite restricted. The domain of blue is limited, and the graph doesn't go beyond this disk of radius 2 in the xy plane, whereas the graph of red seems to go on without limit, and that makes sense based on the formula for the red surface, which has no square roots, no logs, and no fractions that might cause restrictions on the domain. So this is quite a fun program to use, in my opinion. Okay, so let's go back and let's just define a term real quick. Let me invert colors again. The name that we give to a graph of a function of two variables, like we have seen in the previous examples, we call these graphs surfaces. The graph of a function of one variable is called a curve, and the graph of a function of two variables is called a surface. And you'll see that terminology used considerably once we get into chapter 3 toward the end of the course, surfaces. Now, there's another technique that can be used to get an idea of what a function's graph looks like, which I would say is even more useful than the technological graph under certain circumstances. From time to time, you will run into a function of two variables, which is extremely complicated, and the graph becomes so messy that it's sort of hard to even digest the graph that's made by technology. There's so much chaos in the picture that you really can't see what's happening. And when the technological graph is too chaotic to understand, the level curves come in as another visual representation of the graph that can be much easier to actually read and parse. So, a level curve of a function f of xy is the set of all pairs xy satisfying C equals f of xy for some constant C. So what this is saying is that a level curve is a collection of pairs xy, and all of the pairs in this set, if you plug them into the function, they will all give you exactly the same output. They will all give you exactly the same C value. Now, one interpretation of this that's extremely useful is that the level curve of a function is the set of all pairs xy where the height of the graph is this constant C. So a level curve will tell you at all the positions at which your graph has a certain height. For example, if I uninvert colors again, and I go back to my graph, let's use the one in red here, then you can see a collection of points on this graph at a height of, let's say, z equals 2. This band of points are on the edge of this marker-shaped surface, each having a height of 2. So this circle of xy values at this height would be the level curve of this surface, corresponding to a fixed height of 2. It would have a circle shape. Okay. Now, one of these level curves is not especially useful. But when you bunch a collection of level curves together, you get a very interesting depiction of the function's graph, which is called a contour map. A contour map is a collection of level curves, all drawn on the same axes, all drawn together. In other words, a contour map functions like a topographical map for a function's graph. If you've never heard of a topographical map before, then I pulled such a map for, I think this is some state park here on the side, topographical map for the state park. Now on this map, you'll see a selection, a variety of different curves and lines here. And each one of the curves that you see in a topographical map corresponds to a certain height, a certain elevation. So as you look at this map, you can sort of envision a slope coming up from all these different directions. Slope, slope, slope. A slope coming up, forming a mountain whose cliff top is right here in the center. Now we can also see that some of the lines in this topographical map have been marked with numbers, and those numbers on the line are used to indicate what elevation is assumed by all the points on that line. If you're at any point on this blue line marked with the number 6400, all the points on this line have the same elevation of 6400 all the way around. Now, speaking in abstract terms is fine, but let's get some concrete examples to make this a little easier to understand. Let's go ahead and sketch a contour map for that function f of xy equals 4 minus x squared minus y squared. That would be the function that looks like a marker that we graphed in red online. And then let's use a contour map to sketch the graph of f of xy here. Okay, now sketch a contour map with the levels z corresponding to 4, 3, 2, 1, and 0. So that means that if I want to sketch the contour map corresponding to the level z equals 4, I'm going to try and describe the level curve corresponding to z equals 4. I'm going to try and describe all the points x, y, which will give me an output of 4 from the formula. Now suppose that I add x squared plus y squared to both sides and subtract 4 from both sides. That says that if I want a point whose output is 4, then x squared plus y squared has to be 0. So this is in a sense a circle of radius 0, which is just the single point x, y equals the origin. So on the side, I'm going to start to draw these level curves on the same axes. And because the level curves are just equations containing x and y, I'm going to draw the level curves like a topographical map on 2 dimensions using only the x and y axes. And I'm going to put down z equals 0. I'm just going to mark that point at the center, an elevation of 0 there. Excuse me, an elevation of 4. I'm going to mark that point with the corresponding z value. That point has an elevation of 4. Now let's compare that with the graph that we created using technology. Here at this point, in the center, 0, 0, our function does indeed have a height of 4. And that center point is the only point in the picture that reaches that height. Okay, let's go back to the example and let's try the next level, z equals 3. So I'm going to set z equal 3, And I'm going to try and find all the inputs, x and y, which give me an output of 3. Now once again, we can do a little algebra shuffle to say that this must be x squared plus y squared equals 1. In other words, the set of all points that correspond to an elevation of 3 on the graph is the circle of radius 1. So I'm going to put some nice spacing in here, and we're going to create the circle of radius 1 as well as we can. And I'm going to mark that level curve with its elevation. All the points on this curve in our contour map have an elevation of 3. And again, let's compare with our technological graph. Z equals 3 is just about at this level here. And all the points on the marker with that elevation, if I look down at the x-axis to see what points might give us an elevation of 3, it definitely looks like a circle of radius 1 in terms of x and y will give us that elevation of 3 around the rim of this marker. Let's move on to the next level. We can move a little faster now. If we have z equals 2, we need to solve 2 equals 4 minus x squared minus y squared, which corresponds to a circle of radius square root 2, or roughly speaking, 1.4. So I'm going to come in and try and draw a circle of radius 1.4, roughly speaking. And I'm going to mark that with its corresponding elevation 2. And finally, for z equals 1, 1 equals 4 minus x squared minus y squared. That's a circle of radius root 3. So we can roughly sketch that in. That's going to be a little bit closer than before. Mark that with its elevation of 1. And finally, let's go ahead and do the level z equals 0. 0 equals 4 minus x squared minus y squared is a circle of radius 2. So finally, to finish the contour map, decorated with the level curves corresponding to the given z values, we have these 1, 2, 3, 4 level curves here, each drawn in the xy plane on the same axes, marked with their elevation. Now this is, generally speaking, the highest quality graph that I can make by hand, because I am not a particularly skilled artist. But if you like, you can go out to another technological website. Let's go ahead and invert colors again, and let's go out to Desmos. And we can, for example, here in two-dimensional Desmos land, get sketches of the level curve corresponding to z equals 4. It's not visible because it's just this single dot. We can get the level curve corresponding to z equals 3, corresponding to z equals 2, corresponding to z equals 1, corresponding to z equals 0. And this graph might be slightly more informative than the one that we made by hand, because I think it's a little bit easier to see on Desmos that as we are moving away from the center of the circle, the level curves are getting closer together little by little. So it's taking even less in terms of change in x and y values for the z coordinate, the elevation, to drop. That corresponds to the fact that this graph is getting steeper and steeper as we move away from the origin. So you don't have to move quite as far in the x-y direction to see a drop in the z value. Now, we're going to be working with level curves quite a bit more over the course of time, This is just an introduction to level curves and contour maps. And we'll see how we can use them essentially as a replacement for three-dimensional graphs of multivariable functions, just because they are two-dimensional and they tend to be much easier to understand. You don't need to rotate them to try and understand what's going on.